Once a major blaze gets out of control, fire appliances from many nearby areas are rushed to the scene to fight the flames. At this stage, it is principally a matter of preventing the fire from spreading to neighbouring buildings. One question for the planners, however, might be whether the earlier arrival of the first fire appliances could have prevented the fire catching hold at the outset. Most fire calls are for much smaller incidents. A large town may have a dozen such calls a day. But for a typical domestic mishap, the speedy arrival of a fire engine from the nearest fire station is clearly the all-important factor. Now, ideally, to cut the response time to a minimum, one would build a fire station at every street corner. But the cost of such a comprehensive fire service would obviously be prohibitive. In any area, we've got to make do with a limited number of fire stations, and that raises a question. If you're going to build a set number of fire stations in a particular area, just where should you put them to get the best possible fire cover in the circumstances? That's the question we're going to be looking at today. Well, to show you the nature of the problem and the sort of thing involved, let's take a very simple example. I'm going to suppose we have a very simple road network. And supposing it's connecting 3 villages, I'll call them A, B, and C. Now imagine the distance is, let's say, 6 kilometres here from A to B, 5 kilometres from A to C, and 2 kilometres from B to C. And I'll also imagine we're only going to be building one fire station for all 3 villages, so where should you put it? If you put it at A, that doesn't seem too good, because now it's 6 kilometres to B. Doesn't seem much better if you put it in B, because then it's 6 kilometres to A. Obviously, if you're going to put in any of the villages, it has to be at C, because then the maximum distance is this distance 5 to A. And in a certain sense, then, C is the centre of this network. It's the node for which the maximum distance to any other is the least, the minimum. Is that really the best you can do? Well, obviously it's not, because why should you put the fire station in any of the villages? Once you realise that, then I think the answer is pretty clear. You can soon figure out where the fire station ought to be. It ought to be 1.5 kilometres from C along the road to A. Because then you see, what is the maximum distance? 3.5 kilometres to A and 3.5 kilometres to B. This point is what we call the absolute centre of the network. It's the point for which the maximum distance to any of the nodes is a minimum. You might argue, perhaps, that the fire station ought to be somewhere in the middle here, but that's not very sensible. Fire stations have got to be on roads. They've got to have easy access to wherever they're going to go. And throughout this programme, we shall assume that fire stations are being built on the roads of the network. That's a very simple example, but of course, real life isn't going to be that simple. In practice, this problem has attracted a great deal of research, not only in this country, but also elsewhere. And one country where the results of that research have been applied quite a lot in practice is the Netherlands. This is Rotterdam, the largest port in Europe and a major centre of commerce. It has a population of about 750,000. And although parts of the town were largely rebuilt after the war, much of the traditional style of Dutch housing remains. A major feature of Rotterdam is the River Maas, which divides the town into roughly 2 equal halves. Situated near the river are several sites of the old cleansing department, which used to include many of the city services, including garbage disposal and the fire service. In the early 1970s, the city services were reorganised and the fire department became autonomous. Several old fire stations were closed down and new stations were built as part of a new approach to the design of the fire system. Before we look at how the plan came into being, there are 2 things we need to know about the fire service in Holland. Once an alarm is received, the fire crews spring almost instantly into operation. A total turnout time of 1 minute is allowed to get the fire engines onto the road.
De tas 130, tweede instantie, Bakkerstraat nummer 18. Denk aan de uitrukbevestiging.
For the main stations, traffic lights can be controlled from the operations room to allow swift access to the road network of the town. Once on the road, the fire convoy is expected to reach a fire anywhere in the district covered by that station in a time of 6 minutes after the receipt of the alarm call. This is called the first attendance time. As a result of the network study, there are now some 13 fire stations in Rotterdam, and a constant vigil has to be kept not only for fire alerts, but also for points of congestion in the city. We're now in the central control room of the Rotterdam Fire Department, where emergency calls come in from all over the city. And they have a display here on this board showing the current status of the information throughout the city. We can see, for example, these yellow lights here. These are the locations of the fire stations. We have here one of the major tunnels under the river, and over here, bridges across one of the other waterways in the city. Now, of course, what we see here includes the changes made as a result of the study. So to appreciate the reason for the study and the problems they faced, we have to ask just how did things look before they started? And this was the question I put to Dr. Sjoerd Baas, a member of the team at the University of Twente.
Well, back in 1974, when we were asked by the Home Office in The Hague to start a study on the situation in Rotterdam, we found it, as you see it on the map, with the stations represented by red dots. And a serious feature in this is the situation of the stations on the edge of the river Maas. If we take this one, we can see that half of its reach is blocked by the river, and that the other half is seriously hampered by the presence of bridges, which can be a problem for the fire engine to overcome. In order to be able to study using a network model on the city, we first had to develop a system of districts covering the whole city. The first possible choice to do that was to use the districts as they were developed already by the fire brigade. You see them on the map indicated with heavy lines, each district being served by one station. However, there was one serious problem. If, for instance, you see the railway track here intersecting the district, this would cause a serious problem for us to model the response time by a fire engine to a fire call, because it's difficult to pass through that railway track. So we had to refine our system of districts to further develop the network model. So before we come to the precise determination of our districts, I shall try to show you how we developed the network model. In this figure you can have a schematic idea of how the network was developed. You see a set of 6 districts, and in each district we found the roads connecting one major road crossing to represent a central node within that district. Let's think of a fire station here on the network. The fire engine needs, on the average, 1 minute to turn out. If there is a fire somewhere in this district, then we assume, wherever the fire may be, that the fire engine has to pass through the central node of that district. The time needed to get from the station to this central node can be determined by assuming an average speed of 40 kilometers per hour. A fire could take place anywhere in the district. So to have a good measure for the time needed to get to the fire, we choose the worst point within the district, and let's assume that point is here. So the additional time needed for the fire engine to get to the fire address is the time needed to get from this central node to this fire address. And that gives us a good measure of the time between the first moment of alarm and of arrival, being the total of the turnout time, the time to get to the central node, and the time to get from the central node to the farthest point. On this map you can see how our districts were actually constructed. For example, you can see a district here being served by a central node on this point. The major roads, as we determined them, are represented by red lines on this map. Now we had all our information available to develop a computer program to investigate the right locations of the fire stations and the number required.
Now, the problem faced by Dr. Baas and his colleagues at the University of Twente was twofold. You see, on the one hand, they had to decide how many fire stations were needed, and on the other hand, they had to decide where to put these fire stations. Suppose for a moment you'd built a certain number of fire stations. Then there'll be a worst possible case. There'll be a maximum attendance time at some point in the city. And quite obviously, you want to keep that maximum attendance time to a minimum. So you've actually got a minimax problem. Now, the snag is that in order to decide how many fire stations you need, you apparently need to solve the minimax problem for several different possible numbers of fire stations. Well, solving it even once is difficult enough, because you see, since we allow that the fire station should be anywhere on the arcs of the network, you've got an absolute p-center problem. And for a long time, it wasn't really known how to solve it. One place where extensive research on this problem was carried out in the early 1970s was at Imperial College London in the Department of Management Science. A leading figure in the study was Dr. Nikos Christophidis.
In the early 70s, Peter Viola and myself developed an algorithm for the absolute p-center, which was an iterative algorithm that could solve problems with any desired degree of accuracy. In addition to solving absolute p-center problems, it could also determine the value of p, which was needed to solve a particular location problem. For example, the one that was encountered in Rotterdam. This diagram shows 6 villages, A, B, C, and so on, and the roads connecting the villages. The distances are shown next to the roads in kilometers. What is required is to find the number and location of fire stations so that every village is within a distance of, say, 7 kilometers from its nearest fire station. If we look at village A, the fact that a fire station has to be within 7 kilometers of A means that a fire station must be located in the yellow area of the graph. The yellow area is composed of all paths within a distance of 7 kilometers from A. The extremities of the yellow area are shown by markers small a. The yellow area we will refer to as Q of A. Similarly, if we look at village B, we have the region Q of B. Again, the extremities of that region are marked with a marker little b. If we now do the same for all villages and put the markers on the same network, we have this complicated looking network, which, however, contains all the information that is necessary to solve the location problem. The markers break the arcs into a number of segments, segments such as FB, BE, and so on. Whenever two markers coincide, such as for this point here, markers A and C coincide, the segment reduces to a single point. The importance of the segment is that every point within the segment covers the same set of villages. If we look at this segment, any point in that segment covers villages A and B. There are other segments which cover exactly the same set of villages. For example, this segment, and that segment cover exactly the same set of villages as that segment. When we put those 4 segments together, we form a region. The region is shown on the next diagram. It is denoted by QA intersection with QB. That is, every point in that region reaches or can cover village A and village B. As we have seen earlier, when two markers coincide, the segment becomes a single point. A segment that is also a region in the example is this point on arc BC. This region is denoted by QA intersection with QB intersection with QC. It is the only point which can cover villages A, B, and C. We denote this fact by a binary representation of a region. In this case, the binary representation is 111000 to represent the fact that any point in the region covers villages A, B, and C, and does not cover villages D, E, and F. We can do the same for all the regions and associate a binary vector with every region. We enumerate 18 regions. For example, region 7, any point in region 7 covers villages E and F. Any point in region 18 covers villages E and F, and in addition covers village A. This means that 7 becomes redundant, is unnecessary for further consideration in the presence of 18. Similarly, all regions 1 to 11 are dominated by regions 12 to 18. So what is required is to find from the regions 12 to 18 a set that will cover all 6 villages. And the resulting problem is called the set covering problem, which we will represent by a bipartite graph. In this graph, region 12 covers villages B and F, region 13 covers villages D and F, and so on. The problem is to choose the smallest number of regions to cover all the villages. And for this small example, there is only one solution, which is visually obvious, regions 16 and 18. Between those two regions, every village is covered. So in our regional network, we will need 2 stations in the regions corresponding to 16 and 18. Region 16 is a single point region, and region 18 is a segment of arc AE. In the beginning, we have made the assumption that we want to locate fire stations so that every village is covered within a distance of 7 kilometers. In a practical situation such as Rotterdam, traffic conditions may worsen, in which case we may want to reduce the 7-kilometer distance to 6.5 kilometers, and we would like to know what happens to the solution. In that situation, the single point region represented by this point would disappear, would no longer be a region, and it will not be possible to cover all 6 villages with 2 facilities. It would in fact be necessary to have 3 or more facilities. 7 is a critical distance, and the solution corresponding to that distance is the absolute p-center of the graph, in this case the absolute 2-center.
The changes in traffic patterns in Rotterdam were one of the factors the team from Twente University took into account in their study. And it was the absolute p-center problem which was important. Now, Dr. Christofides has shown us how to recognize an absolute p-center when we find one. But if the traffic conditions are indeed variable, how do we set about finding the p-centers and the critical distances in the general case? We can see the technique if we take the simple network we used at the beginning of the program. If we let lambda denote the maximum distance from a fire station, this was 7 kilometers in Dr. Christofides' example, then with lambda equals 3.5 kilometers, we had the absolute 1 center of the network. If lambda was 0, we can see that we should have the absolute 3 center. There would then be a fire station in each village. must therefore be that there's a value in between, value of lambda somewhere from 0 to 3.5, which will give me the absolute 2 center. We don't know where. Let's be systematic. Let's increase lambda step by step. Let's take a small value of lambda and see what happens. I'm going to get a region around A, and I'm going to get a region around B, and I'm going to get a region around C. And if you look, there's still only the possibility of serving each of the villages from one region. And so I still need 3 centers. And in fact, as I increase lambda, nothing's going to happen until 2 of the markers coincide. When is that going to happen? Well, if you look at this, which is the shortest side, I think you can see, if I move these 2 closer together, they will eventually coincide, and they'll coincide when I reach the midpoint. And there we'll have a double marker. So for the first time, we shall have the possibility of serving 2 of the villages with just 1 point. And if, in fact, we look at the bipartite graph corresponding to this situation, we now have this 1-point region, which will, in fact, serve both B and C. This will happen at the midpoint, so it happens when lambda is equal to 1, and that's the smallest possible value of lambda, and so therefore what we've got is the absolute 2 center. If the network had been bigger, we could go on to find 3 centers, 4 centers, and so on. And that's the basic technique. It's the smallest value of lambda which will give you what you want. So, okay, we know how to actually find absolute P centers. What happens when the algorithms were applied to the situation in Rotterdam?
The computer told us that we need 6 fire stations in the north of Rotterdam and 5 fire stations in the south of Rotterdam. To give you an example, the computer told us that this station better be moved to that spot, and this has actually been done. Another advice deals with this station, which should be moved to that point. This is still under consideration, but it will be moved in the forthcoming years. There were indeed some newly built stations in Rotterdam, and we decided not to move them. However, we had to do the part of the program again in order to find out what the consequences is of this decision. And we found that we needed an additional station in the northern half of Rotterdam and 1 additional station in the southern half.
What we've seen in this program is an example of a problem which is not only of great theoretical interest, but obviously of great practical importance as well. The solution was not easily come by, but we've seen that when it did come, the breakthrough relied precisely on the fact that we had modelled the problem as a network problem.